In this video, we're going to do some more examples involving rational expressions. So simplifying rational expressions, working with them to multiply, divide, add, subtract, etc. So just how to work with rational expressions. So let's start with part B here. So we're reducing this rational expression into lowest terms. Okay, so basically we want to simplify this expression. So in order to do that, we want to cancel any common factors. Okay, it's hard to see if there's any common factors here, but I notice that the top is a difference of squares and the bottom is a sum of cubes. Okay, so let's just rewrite that. So the top is x squared minus 3 squared, and the bottom is x cubed plus 3 cubed. So if we remember those formulas from the factoring section, the top is going to factor as x plus 3 times x minus 3, and the bottom is going to factor as x plus 3 times x squared plus 3x plus 3 squared, which is 9. Okay, now I can see that we have a common factor. So x plus 3 is in the top and the bottom, so we can cancel it out, assuming that x plus 3 is not 0. Okay, so we might want to make a note of that, but that's more important later on. So we're left with x minus 3 on the top, and on the bottom we have x squared plus 3x plus 9. Now you might want to think, okay, can we factor the bottom more? So if we could, we would want two numbers that multiply to give 9 and add to give 3. So to multiply to 9, we have 1 and 9, and 3 and 3. Okay, so this sum would be 10, this sum would be 6, or the negative versions, and then the sums are going to be the negatives here, so you never get a sum of 3, so this bottom polynomial is prime, so it doesn't factor any further. So this is how we would leave our answer here. Okay, what about when we're working with fractions? So in part B here, we have one fraction divided by another fraction. Okay, so when you're dividing fractions, what you want to do is flip the bottom one and multiply instead. So I'm just going to rewrite the bottom one in the opposite order. Okay, so I flip the bottom one and multiply. And now I just want to simplify this expression. So when we multiply straight across. So I'm going to have 3 plus x times 9x cubed divided by 3 minus x times x squared minus 9. Okay, now x squared minus 9 is a difference of squares. So we could actually factor it to see if there's any common factors. Okay, so x squared minus 9 simplifies to x minus 3 times x plus 3. Now x plus 3 and 3 plus x are actually the same. So those cancel, assuming that x plus 3 is not equal to 0, or x is not equal to negative 3. And then we just have 9x cubed on the top, and the bottom is going to be 3 minus x times x minus 3. Now if you wanted to simplify this further, I didn't leave myself a lot of room here, but 3 minus x, I'm just going to write it on the side here, I'll put it up here. 3 minus x is actually negative x minus 3. So on the bottom, we actually could have negative x minus 3 all squared. Okay, and that negative could go on the top, on the bottom, just out front. It's the same either way. Oops. But yeah, so it's x minus 3 all squared. I think those are the only, oh no, there's a couple more here. So with addition and subtraction, we need to make the same base. Okay, so we need to have a common denominator. So similarly, what we just did above, I'm going to write it here again. So 6 over x minus 1, these bottoms, so x minus 1 and 1 minus x, they're very similar. Okay, and in fact, 1 minus x you could write as negative x minus 1. Okay, now that negative can come out front, so we could actually replace this with a plus. Okay, so the negative here and the negative here combine to make a positive. Now I have a common denominator, so I can just add the tops. So this is going to be 6 plus x over x minus 1. And that's how we can't simplify that anymore. Okay, so another one. Here we need a common denominator. So it looks like that they have some common factors in here. So our common denominator, maybe I'll write that here. The common denominator is going to be x plus 2 squared times x minus 1 squared. So it's the least common multiple of these two denominators. So in order to get that on both, on the first one, I'm going to write this down here. Okay, so on this first one, I already have the x plus 2 squared, but I only have one x minus 1. So what I need to do is multiply by x minus 1 over x minus 1. In the other one, I only have one x plus 2, but I have both of the x minus 1s. So what I want to do, which I don't have room for, so let's make this minus a bit smaller. What I want to do is multiply by x plus 2 over x plus 2. Okay, so these, remember, are our fancy ones. Okay, so you're always allowed to multiply by 1. Okay, so if we do that, we're going to have 2 x minus 1 on the top, and then we have x plus 2 squared, x minus 1 squared, and then over here we're going to have 6 times x plus 2 over x plus 2 squared times x minus 1 squared. So now I have the same bottom. I can put the tops together. So I'm going to have, and I'm going to expand them. So the 2 has to go in, and the 6 has to go in. So it's going to be 2x minus 2 minus, now it's important to put this bracket here, so 6x plus 12, because that minus, I have to subtract everything on the top up here. Okay, so that's going to be 2x minus 2 minus 6x minus 12. All over x plus 2 squared times x minus 1 squared. So putting these like terms together, so I have 2x minus 6x is minus 4x. And then minus 2 minus 12 is minus 14. And then finally, I could take out a negative 2 here so that I get 2 x plus 7, and that's over x plus 2 squared times x minus 1 squared. So let's just put that in a box so we can see that would be our final answer. And then the last thing that we talked about in this video, but I did both the examples and the notes, were rational expressions involving complex fractions. So there's fractions within the fraction. So in class, when we talk about rational expressions, I'm planning to do at least one extra example of this, just to make sure we're comfortable with things that look like this. I don't want them to be scary for anybody. So that will be in class. So we've covered all the examples so far. So remember, the main thing you need to remember when you're working with rational expressions is that all of the regular fraction rules apply when you have polynomials in your numerator and denominator.